Hey guys, have you ever wanted to create a landing dragon effect? Then you came to the right place. In this tutorial we're going to use the Rebelway challenge file to create an excellent dragon landing. Stay tuned and watch the tutorial. Guys, do you want to join a really nice server? We have tons of different channels. We have effects, modeling, loop dev, compositing. We will have resources for every type of discipline. So hop in and have fun. I also have a Patreon page where you can support me. I have every single file, I have polls, I have even some tools, guidance. So if you are interested, you may have a look. Thank you. Okay guys, so we are in the Rebelway scene. This is a really nice file, which I'll leave in the description how to edit for free and how you can hop into the challenge. So this is a scene or a whole bunch of scenes where there's a dragon involved, and you have to create all the effects on the shots you want, of course. And the first shot, which is this one, if you hop in right here, you will find a bunch of shots. Each one has its own identity, but the first one is basically a dragon landing, and you can create a bunch of things. For example, when they open the mouth, you can make them scream and launch some fire stream, fireballs, lava, electricity, whatever you want. But I'm more concerned about the landing, since the camera, as you can see here, it has a really nice movement where you can take advantage of and create like a smoke landing effect. And how can we create that procedurally? So this is how it begins. First of all, and most importantly, we need to create the collisions. So we will start by importing from the master scene, the scene 01, the dragon, plus the animation of this character right here. But we're going to split it based on the names, path dragon. As you can see here, we have on the path the dragon name right here. We're going to convert this into polygons so we can actually select each and every one of these faces, and we're going to make a trail so we can start having some velocities. As you can see here, this is without and this is with velocity. This is going to be set to the points. As you can see here, it moves as the dragon moves, and it's going to be on central difference, so it's more accurate. This is the out full dragon, the original. It's like the raw version of it. And as you can see, for example, the wings are flat. They are literally flat. So we need to make some thickness out of it. So we're going to split again based on the wing. We have the wings. We're going to add some normals, like so. And we're going to poly extrude and create a back out of it. And since these are actually reversed, as you can see here, they are reversed. We're going to use a reverse now to take them back to normal. So then we are going to create new normals on vertex so we can have a nice shading. These are basically a split on the body. I just double click and selected the whole body right here. For example, if I do this, double click and split, it's exactly the same as this node here. So I'm going to split all these little shapes because I don't need them. So I'm merging these two guys, and then I'm using a collision source. We are going to fill the interior. I'm going to use a voxel size of 0.2. On the right side, we're going to do a file cache with these settings, and we're going to save it to disk so we can load it faster. As you can see, we don't have a velocity because we're going to create the velocity outside of this collision. We have the collision poly here. Very nice. We have all the velocities. Everything is cached out. This is the most basic step of a collision. So we're going to create the velocities right now. So we have the out or full dragon with the velocities right here. And we're going to do a time shift on the first frame, 10:01. And we're going to use a bunch of scatter with these output attributes right here. These are the settings. Only a bunch of points and no relaxed iterations. And we're going to point interpolate from the source to the character. And as you can see, it's a perfect kind of pointer form, which also translates the velocity. Very lovely, right? And we're going to visualize This is very important because we need to have full control on how we want this to look. The visualize is just BHCD, and we're going to use a ramp based on what? Based on a fit of what? Of the length of, or the magnitude of the velocity, which I found a very nice value being 0 to 50 and 0 to 1. So we are basically normalizing the magnitude. And as we can see, we have the dragon with all these colorful colors and which represent the velocity. I use an RGB palette so it's easier to see. And this is the null which represents this section. So we're going to create two fields out of it. First of all, the small velocity and then the big velocity. The big velocity has a difference where I'm going to show you once we are at the large velocity. So what happens here? The small velocity is going to be rasterized based on this. We're going to use a natural rasterize, select the B small, which is this one, B small, and we're going to use a particle scale of 0.65 and 2.5 on coverage scale with a normalized clamp. We could use velocity blur, but we actually don't need it. And the formula here is basically I'm copying the parameter, pasting it here, paste relative reference, and I'm also copying this one, and then I'm using a multiplication sign, as you can see right here, and pasting the relative again. And at the end of it, I'm using a divided by 4. This is a good representation of the two, the scale and the coverage scale. They work together on a really nice flow. So we're going to do the same with the large velocity, but instead the vertex scale is going to be very big, because the most important thing about large scale simulations is to have large scale interactions. And this dragon is very big, it's like 50 meters long. So we need to have big interactions of velocity. If we do a volume trial, we will see that if we add a time shift right here, this is only to visualize, we're going to set this to 1088 and do a box and then some ISO offset with some scatter inside. We will see how this velocity looks, point to trail and required velocity. And it looks very, very large. As you may see here, they are simply very large. I'm going to show you the dragon as a reference. So this is going to be affecting everything on its surrounding. But if we do it with a small v, you will see everything is very small and near the body. Very cool, right? I'm going to use more points so we can see this better. And look at this. This is close to the body. This is far from the body. We'll use these two velocities. We're going to merge them, and these are going to be the out dragon velocities. Now, the most important step is on the FX smoke landing SC01. What I'm doing here is creating a grid and expanding it where the dragon, as you will see here, is. Nothing fancy, but I'm scattering some points. Again, with no relaxed iteration. And what I'm doing with the dragon is, hey, do a time shift, scatter again. This is the same setup as before. Interpolate and visualize the velocity. I copied here because I wanted to have everything together. This is the same setup as the other geometry, so I just copy and paste it. And we have two places, the raw velocity and the distance. I'm going to start by the velocity, which is kind of easier to understand. So what I'm doing here, first of all, is creating the IDs of this dragon. Secondly, I'm selecting the ground, which is here, to have it as a target. So this node in particular is very important. It's the source and the heart of this solver. So what I'm doing here is to creating an array of points based on the pcopen. Pcopen is a way to read points, a point cloud, right? So I'm reading every single point and based on a radius and caching all the information on its surroundings. So I'm grabbing the first input, which are the points, and saying, hey, what's your position? And compare it with my position based on this radius. So I'm comparing the position of, I don't know, X point on the dragon to X point on the grid. And I'm selecting a bunch of points, perhaps in this case only 2, so we can later on interpolate. And how are we going to interpolate? Based on the PC filter. The PC filters grabs my grid, it needs a handle, this is the handle, and it's saying, hey, you know what, based on your configuration here, interpolate the points where you seem fit. And this is going to be like a blur. And if we pay close attention, it's kind of as a ray, right? Because the closest point is directly the one you have under your dragon. You will see if we have more points, it's going to be more detailed. If we have less points, it's going to be faster. You will see it's exactly the same, and you will ask you, hey, why do I need to have the dragon on the ground? Well, one thing that you can have in mind is that, hey, I know the distance from these points. They are exactly the same points because I have the ID, and I can make some calculations out of it. So let's compare A with B. And what I'm doing here is kind of calculating the distance. What is the distance from point A to point A on a different scenario? And I'm calculating this. These are all the distances. It goes from 0 to at the very top right here to 47 meters. It's a very big dragon. And what I'm doing here, since I already have the points on the ground, these are the points on the ground, I have this point is to first initialize the velocity to 0 and transfer these velocities. You will see everything is transferred right here. I'm going to exaggerate a little bit the points velocities, but basically they're all here. And you will see, based on this condition, I'm going to set in the velocity and a really big blend, that well, from some moment everything starts to clamp out. So what I need to do is to first visualize and see what's going on. Let's see what's going on. What happens if I increase the blending? You will see I have these rough edges, and this is a problem because it's going to create a rough source, and we do not want a rough source. So let's go back to normal. This is already okay. Let's do the same trick we did here with the position, but for the velocity. So let's delete some points, some random points. From 1000, I'm deleting 980. Okay, so basically these are the same points. What I am going to do here is to interpolate the velocity we have here with the velocity we have here. So how do we do this? Again, with this lovely solution, but instead of interpolating the velocity, instead of interpolating the position, I will interpolate the velocity. That's the only thing I did. So let's see how it looks. Oh my god, this already looks way better than this. This is all clamped, all noisy, and this is perfect. So let's have a look. What happens if right here I decrease the points? I'm starting to lose detail, and the more points I have to look at, the more soft it's going to be. And these are the radius. The less radius I have, basically the shorter it's going to be. There we see. So again, it's soft, but the radius is not that big. So let's go back to normal and let's compare. Look at this. Everything is very smooth. It doesn't matter. It doesn't clamp anywhere. This is even soft. So it's great for our needs. This is the raw velocity. It doesn't matter if the dragon is very high. Where is the dragon? Okay, it doesn't matter if the dragon is at the very top or at the very bottom. The velocity is kind of similar. So we don't have a way to control the magnitude right here. So let's do the following. Let's make the same process, the same idea with the points. Let's do exactly the same distance calculation, but in this case let's make a really long distance, imagining the dragon is very far away. But let's transfer this one. Let's transfer the distance and let's visualize not the velocity. It's called velocity, but it's not velocity, it's distance. and let's use the lines of the distance, which it doesn't matter if I'm using the lines because it's a float, and let's calculate from 50 to 1 meter. So the closer you are, the higher value you will have. And this is even worse than before. Look at this. Everything is so clamped, so noisy. I really don't like this. So let's do the same trick as before. And let's see, with the same trick, only using distance instead of velocity. Let's see how it looks. Amazing. It's literally very smooth, and this is a very nice value to have. So let's actually copy the distance, and let's use a small calculation right here, and let's visualize this. So this calculation is basically saying, hey, multiply based on your distance from the minimum to a max all. I'm using, hey, the max distance is 200 meters roughly, and the minimum distance you can have is, well, 0 because you're standing on the ground. This is all it's doing, and I'm using a ramp because look at this. Where I have a long distance, for example, at the very beginning, I really didn't want to have much multiplication. This is basically normal. So you can control how much velocity I have when it's higher or lower. So this is a very nice control factor. Look at this. I can say, hey, I'm very close, so let's have more. So I am very close, so let's have a lot of velocity where I'm closer. And I could do that around. I don't know why, but I could, for example, multiply it lower. So let's lower this, and now I don't have velocity where I'm near the ground. So you have a lot of possibilities right here. This is perfect for what? To create a source. So let's use this out velocity. Let's do the following. Look at this and pay attention. I'm saying, hey, I want a direction. The direction is going to be upwards, right? So the velocity is the same. So the velocity is going to be upwards. I still don't have a velocity, it's only vector. And the density is going to be, hey, the same. This doesn't matter. I mean, it's velocity, but it could be instead density. I just copy and pasted the code. And I'm saying, hey, what's your velocity length? Okay, 0 to 50. Well, so I can do a ramp and create velocity out of these values. The more velocity you have, the more likely I'm going to have density. If I don't have velocity, like these blue areas, I don't want density. There's no reason to create dust there, right? So how does it look? Let's watch both of them together. So if I control this, I'm going to select more and more and more velocity to create density, unless it's 0, of course. If I go the other way around, I'm only going to generate velocity on the faster points. And what I'm doing is to have a simple velocity. I'm going to learn the already existing velocity right here. As you can see, we have some velocities with the up vector. The up vector is going to be this blend, because I did want to animate something at the very beginning, going upwards and then going back to normal. That's about it, there's nothing else. And we're about to finish on the DOP network. The DOP network is not much complex, to be fair. Let's hop in, let's go to the first frame. And what we can see, I'm going to just show you the pyrobake with the dragon. Let me load this dragon. So what's going on here? Let's put the light. Well, basically what's going on, let me just tick this because I forgot. What's going on is, hey, I'm creating a Paris solver sparse. You could be using the small sparse, it doesn't really care. And I'm using a ground plane, so it collides, there's nothing else. And a smoke sparse, as everything is normal at this moment. So watch this. I'm sourcing the density. This is our density we created here. These are the values, B1, temperature, and density. And I'm enlarging this so it can always be inside the geometry, or inside the bounding box. Basically what I did is sync and then source. That's all it didn't change. I didn't change anything. And the second one is the big velocity. Did you remember that I said, hey, if you want to have large scale simulations, have large scale interactions? And I loaded from the out dragon B only the source, which is big, and I set it to, hey, go to the velocity of the simulation and set this to 0.3. I'm going to unplug this for a moment and I'm going to show you that this works. I'm creating velocity here, and as soon as the velocity of these wings interacts, it's going to move the whole simulation. The wing is already moving this. This will start moving as long as it goes upwards. You will see here the tail makes a whip. Everything is automatic. We are not controlling anything here. It's like a natural movement, which is very nice. Apart from this, what I'm doing is to creating some microsolvers. The disturbance is based on the speed, and the speed is created here on calculate speed. I'm also having a dissipation of 0.1, and I'm saying, hey, that vection method is BFECC and clamp. Basically, clamp BFECC is the best method, and the clamp 2 is better than the modify Mac Cormac. It looks better, just use it. The gas disturbance is set to speed. I just used a remap if I wanted to somehow remap this. The stronger the velocity is, the more noise I'm going to have, and the less there. The settings are block based to set to 0.4, nothing else, and I'm using the collision just so we have a collision, nothing else. I'm not enlarging this. We can probably visualize it right here. If I go here and select collision, you will see the ground, and when the dragon interacts with the bounding box, we will see the dragon collision. Hi guys, I hope that you really enjoyed the video. If you liked the video, please leave a comment, subscribe, and stay tuned for more videos.